In classical mechanics, now we will deal with the problems of a very important chapter which is related to the collisions and or you can say interactions or scattering. Actually in this chapter we will learn about the two frame of references which are known as laboratory frame and center of mass frame. Actually, in many physics problems, the choice of reference frame can greatly simplify the analysis of interactions and collisions. The center of mass frame is particularly useful when you are studying collisions or interactions between multiple objects. And you know that this coordinate system or this frame actually allows for a clear separation of translation and relative motion. So the concept of center of mass frame and how we can deal with the problem of collisions and or you can say scattering or interactions between the two objects or more than two objects can be dealt. These all things we learn in this chapter. Apart from this, we also learn about the concept of central forces and collisions in central forces, particularly Rutherford scattering. Okay, so this is a very important chapter for you, and this chapter is equally important for the students of different levels. This chapter is in the syllabus of MJC semester 1 and also in part 3 honors of physics in several universities and in PG semester 1 too. So this is a very important chapter, and in civil services examination in physics optional, this Rutherford scattering is very important. Okay. But before knowing the concept of these things, first of all, we will learn about the two reference frames which are called laboratory frame and center of mass frame. Actually, our prime aim is to know about the center of mass frame. But for knowing about the center of mass frame, you must have a knowledge of center of mass of a system. Definitely you have learnt about this center of mass in your lower classes in 11th level. But just for a revision, I am repeating the things so that it will be easier to deal with the problem of this chapter. Okay. So before knowing what are laboratory frame and center of mass frame, I am just introducing the idea of center of mass of a system. And for this, you can see this figure. I have considered a system of discrete particles, although center of mass is also defined for a system of continuous mass distribution. But here I am talking about only the system which have discrete mass distribution. So I have considered here there is a system of particles consisting of n discrete particles, and the masses of those particles are m1, m2, so on, mn. Okay. And I have considered a coordinate system represented by the coordinate axes ox, oy and oz, as you can see in this figure. And relative to the origin of this coordinate system, I have shown in this figure that this r1 is the position vector of the point mass m1, r2 is the position vector of point mass m2, and rn is the position vector of point mass mn. Okay. Now if we consider that there is a point whose position vector is this capital R, and this point is called the center of mass of the system. Then how this R can be defined? Actually, center of mass is a point whose position vector R will be defined as the sum of the products of the masses of different particles and their respective position vector and divided by the total mass of the system, or you can say the sum of the masses of individual particles. So you can see I have shown here that position vector R, which represents the position vector of the center of mass of this system. This capital R represents the position vector of the center of mass. Then this R is defined like this. This is m1 times r1 plus m2 times r2 plus mn times rn and divided by m1 plus m2 plus so on plus mn. Now in brief, by the use of sign of summation, you can write that this is summation mi divided by summation mi. Here Ri is the position vector of any ith particle and mi is its mass. But this summation mi, which represents the sum of the masses of the individual particles, this has been actually written as capital M, which represents the total mass of the system, because when you will add the masses of the different particles, you will get the total mass of the system. So in this way, by the use of this equation 1, we define the position vector of the center of mass. Okay. Now if you consider that the origin of our coordinate system coincides with the center of mass, it means you consider that this point, which is center of mass of the system, this is at the origin, or this is treated like origin. So in that coordinate system, the position vector of center of mass will be what? That will be simply 0, because in that coordinate system Cm is already at the origin. So the position vector of origin with respect to origin, same origin, that will be 0. So if you consider that the origin of the coordinate system coincides with the center of mass, then its position vector, this capital R, will be equal to 0. Now see from this equation 1, if R is 0, that means summation mi Ri over capital M, this will be equal to 0, because this is equal to R. And if it is 0, then this summation mi Ri will be equal to 0. Now see, what is this summation mi Ri? Actually, when you multiply mi Ri, you get the moment of mass of the ith particle with respect to the center of mass. Okay, and when you sum up all these terms, then you get the sum of the moment of mass of all particles around the center of mass, or with respect to the center of mass, and you can see this is equal to 0. So in this way, this condition is just the defining equation of the center of mass. So in this way, we define the center of mass as a point in a space about which the vector sum of the moments of mass of all point masses is equal to 0. So in this way, you can define the center of mass of a system. That center of mass of a system is the point about which the total moment of mass of the system, or you can say the vector sum of the moments of mass of point mass around that point is equal to 0. Okay, I think you have learned what is this center of mass. Okay, now we will define the velocity of center of mass. As you know, the position vector of center of mass R, and you know when the position vector is differentiated with respect to time, then we get the velocity vector. Okay. So we can easily define what will be the velocity of this center of mass. If you denote the velocity of center of mass of the system by this capital V denote the velocity of center of mass. And since capital R is the position vector of center of mass, so velocity of center of mass will be simply equal to dr dt. Okay. But you can see since R is equal to this much, so we will differentiate the RHS of this equation. You can see here. Now m1, m2 and so on, mn are constant factors. So this derivative will be simply m1 times dr1 by dt plus m2 times dr2 by dt plus so on plus mn times drn by dt. Okay. But what is this r1? You have seen that r1 is the position vector of first particle, that is the particle of mass m1. Similarly, r2 is the position vector of mass m2, rn is the position vector of mass rn. So when you will differentiate r1 with respect to t, you will get the velocity of first particle having mass m1. I have denoted that velocity by v1. So the first term m1 dr1 by dt can be written as m1 v1. Similarly, dr2 by dt, this is velocity of the second particle, which has been denoted by the symbol v2. So the second term will be m2 v2. And drn by dt, this is velocity of the nth particle, and that velocity has been denoted by the symbol vn. So the last term will be mn vn. So you can say that velocity of center of mass, which is capital V, that will be equal to m1 v1 plus m2 v2 plus so on plus mn vn, and divided by total mass of the system, which has been denoted by capital M. Okay. Now again you can write this expression like this. This is summation mi vi divided by capital M. Okay. Sorry, I have been caught by cold, so don't mind. Now, as I have told you that these v1, v2, so on, vn are the velocity of the individual particles. So if you want to find the velocity of center of mass, you can use this equation too. You have only to multiply the velocity of individual particles by their respective masses, and after that you added them vectorially and divide the sum by the total mass of the system. Then you get the velocity of the center of mass of the system. Okay. Now after getting velocity, we will find the momentum of the system. As our system consists of n particles, and each particle you have assumed are in motion. Since momentum is an additive property, so if your aim is to find the momentum of the system, what you will do? Actually, when we will sum up the momenta of all individual particles vectorially, then we will get the total momentum of the system. So if you consider that these P1, P2, so on, Pn are the momentum of individual particles of the system, then the vector sum of P1, P2, so on, Pn will give you the momentum of the system. I have denoted the momentum of the system by this capital P. So capital P, which is momentum of our system, that is equal to P1 plus P2 plus so on plus Pn, where all these small P1, P2, Pn denote the momentum of the individual particles. But what will be P1? That will be M1 V1, P2 will be M2 V2, Pn will be Mn Vn. Okay. So momentum of the system, capital P, this is M1 V1 plus M2 V2 plus so on plus Mn Vn. But let us see this equation 2. This sum m1 v1 plus m2 v2 plus so on mn vn, that will be simply equal to capital M times capital V. Okay, capital M times capital V. So you can write this P is equal to mv. But what is m? M is, you know, mass of our system, total mass of our system, and v is the velocity of center of mass. So if your aim is to find the momentum of the system, there is no need to know the momentum of individual particles. You can use this concept. You have only to multiply the total mass of the system by the velocity of center of mass. That product will give the momentum of the system. So I have written here, you can see that momentum of the system is equal to mass of the system into velocity of center of mass. And that's why this center of mass is treated like a point which represents the motion of whole system. So the whole system can be replaced in calculation by the point mass whose mass is equal to total mass of the system, and it is located at the center of mass. So center of mass is a point which is just equivalent to whole system if you assume that the mass of the whole system is concentrated at that very point. Okay, so for getting momentum of the system, we have to know what is the velocity of center of mass, and that velocity will be multiplied by the total mass of the system, and that product will give you the momentum of your system. Okay, now after getting momentum of the system, you can apply the Newton's second law of motion for dealing with the dynamical problem to write down the equation of motion of our system. So in case of a system of particles, if your aim is to write down the equation of motion, you have not to think about the individual particles, but you have only to think about the center of mass, because the center of mass represents the whole system. Okay? As you know, according to Newton's second law of motion, the net external force, mark it, net external force acting on the system is equal to the rate of change in momentum of our system. Since this capital P represents the momentum of our system, so if F is the total external force, mark it, I am talking about only external force. If F is the total external force acting on our system or applied on the system, then this resultant external force in accordance with Newton's second law of motion will be equal to dp by dt, where P is the momentum of the system. You can see this equation 3, that momentum of our system is what? This is mv, where m is the total mass of the system, v is the velocity of center of mass. As total mass of the system, this capital M is constant, so it is outside of the differential operator. So this net external force applied on this system of particle will be equal to m times dv by dt. Okay, where this capital V, you know, is the velocity of center of mass. Okay, and dv by dt, this will give you the acceleration of the center of mass. Okay, so you can write the equation of motion like this. This is F equal to m into acm. This is a very remarkable equation. If your aim is to write down the equation of motion of a system of particles, the system consists of more than one particles, and you are going to write down the equation of motion, you have to think about the center of mass. Okay, not you have to think about the individual particles. Simply multiply the mass of the system with the acceleration of center of mass, then you will get the total external force acting on your system. Actually, in case of a system of particles, the internal force also acts between two particles. Let us say this is ith particle, this is jth particle, then these two particles will interact with one another by a force Fij, which is internal force. But when you will sum up these Fij, these will cancel out in accordance with the Newton's third law of motion. So, when you talk about the system of particles, then in your calculation, in net force, only external force comes into the picture. The internal force cancel out. So this F represents only the external forces acting on your system. Okay, and this represents the equation of motion of our center of mass. Now let us consider there is a system which is force free. It means you are talking about an isolated system. When you say isolated system, that means the system which is free from the external interaction. No external force is acting on our system. So when this F will be 0, what will happen? You can see the different things in accordance with equation 3, this will be equation 4, not 3. Okay, so you can see if F is equal to 0, and you have seen that F is equal to dp by dt, so this dp by dt will be 0, and if dp by dt is 0, you know P will be constant. So if no external force acts on the particle, or you can say that the resultant external force applied on the system is 0, or our system is an isolated system, in that condition, the momentum of the system will remain conserved. This is actually the principle of conservation of linear momentum. And if momentum is conserved, you know momentum of the system is mv, and this mv will be constant. Okay, but m, which is mass of the system, that remains constant in classical mechanics. So it means v will be constant because m is already constant. So in absence of external forces, the velocity of the center of mass is constant. What does it mean? It means when net external forces applied on the system is 0, then the center of mass will be either at rest or in motion with constant velocity. Okay, or in motion with constant velocity. And if velocity is constant, you know dv by dt will be what? That will be 0. But dv by dt is acceleration of the center of mass. So acceleration of center of mass will be 0. So when we talk about the isolated system, in that condition, you can say that momentum of such system will be constant. Its velocity of its center of mass is constant, and acceleration of center of mass of that very system is 0. Okay, so I have mentioned it here. You can see that in absence of external forces, the center of mass is at rest or moves with constant velocity, and its acceleration is 0. Okay, actually this criteria, that is when you talk about the isolated system, this is very important. This will be used as a defining condition or defining equation of the center of mass frame. Okay, so after getting this elementary idea of center of mass of a system, now we will see what are the laboratory frame of reference and the center of mass frame of reference. Okay, actually in previous lectures you have learned already about the reference frames. Okay, and you have seen that there are two types of frame of references, inertial frame and non-inertial frame. And when you say inertial frame, that means a frame in which law of inertia, that is Newton's first law of motion, is valid. And you have learned that an inertial frame is either at rest or it moves with constant velocity. Okay, On the other hand, non-inertial frames are accelerated frames. We have learned all these things earlier. Okay. Now, this when you talk about lab frame means laboratory frame. This is an inertial frame. Actually, lab frame is defined as an inertial frame which remains fixed with respect to an external observer. When there is an observer standing, let us say, particularly in your laboratory, and the observer says that there is a reference frame attached to the laboratory, and observer is already standing in that very laboratory, then such a frame is called laboratory frame. So with respect to that observer, that fixed observer, the laboratory frame is at rest. So it is an inertial frame. In brief, you can say a laboratory frame is nothing. This is a static frame. This is attached with our laboratory, and the observer is also in that laboratory. So with respect to the observer, the laboratory frame is always at rest. Okay. So in this frame, when you talk about the motion of any object, the motion is described with respect to the observer standing in this frame. Okay. So remarkable fact is that this laboratory frame is simply a coordinate system attached with the laboratory, and the observer of this frame is standing in the same frame. Sorry. Okay. Now we talk about the center of mass frame. Actually, center of mass frame is also an inertial frame. But we assume that this is a frame which is attached with the center of mass of the system. If this is center of mass and you imagine that there is a reference frame, let us say S, and it is attached with this center of mass, and this is the center of mass of a system on which no external force is acting. It means you consider the center of mass of an isolated system, not a system on which external forces are acting, but we consider a reference frame attached to the center of mass of an isolated system, isolated body. Then such a reference frame will be called center of mass frame. Okay. So if you consider that this is an isolated system and this is the center of mass of the system, and we imagine that there is a reference frame attached to this center of mass of the isolated system, then such a reference system is called center of mass frame. Okay. As in this case, you know, the reference frame is attached to the center of mass of the isolated body. Okay. And you have learned that the position vector of the center of mass with respect to the when the origin is fixed at the center of mass, that is 0. So you can say that in C frame, center of mass frame is also denoted by C frame. So in C frame, the position vector of center of mass will be equal to 0, because the origin of the center of mass frame is already at the center of mass. So R will be equal to 0. But if R is 0, what will be the velocity of center of mass? Since velocity of center of mass you know is dr by dt, but R is 0, so this will be also 0. It is obvious that you are considering the center of mass as a frame and you are talking about the velocity of center of mass in that frame. So velocity of any body with respect to itself is always 0. Okay. That's why we simply say that in center of mass frame, the center of mass is always at rest. Okay. Always at rest. So velocity of CM in CM frame will be equal to 0. And if V is 0, you know the linear momentum of the system in center of mass frame, this will be also equal to 0. And this is the criteria on the basis of which we define the center of mass frame. Actually, you can see that in CM frame, momentum of the system is 0. That's why we call that this C frame as a frame in which momentum is of the system is 0. And this is the reason that the C frame is called zero momentum frame. Center of mass frame is called zero momentum frame because in this frame the momentum of our system is 0. Okay. So this is just an introduction to the center of mass frame and the laboratory frame. Our prime aim is to discuss the collision between two particles, particularly the two-dimensional collision. One-dimensional collision you have learnt in the previous classes, your lower classes. But in here we will see actually the two-dimensional collision or collision in a plane between two objects. Okay. In laboratory frame and center of mass frame. You will see that actually when we will deal the problem of two-dimensional collision or a scattering in center of mass frame, the concept will be very clear to you. We will get more information and that information will be more informative. Okay. So definitely you should watch the forthcoming videos on this chapter. Then you will see how the concept of this reference frame, that is center of mass frame and laboratory frame, are applied to deal with the problem of collisions, particularly collisions in two dimensions. Okay. Thank you very much.